Section 1.1, example 1.4, approximating the area under the curve. Use both left endpoints and right endpoints, left endpoint approximation, right endpoint approximation to approximate the area under the curve for f of x is equal to x squared on the interval from 0 to 2. So we want to use n equal to 4. Let's first start with graphing this. We want to make sure that we emphasize the area 0 to 2. N is equal to 4. We'll talk about that here in just a sec. So I'll do this off camera just so we could not have this as a 50-minute video. Wow, what a beautiful graph. So use the left endpoints and right endpoints to approximate the area. We want to use n equal to 4. What this means is we want to partition our graph into 4 different places. So I kind of made it a little convenient here already. We broke it up into looking at 1, 2, 3, 4 pieces coming from 0 to 2. So the area we're approximating is going to be this area right here. So this area right here, we're trying to find the area under the curve or between the curve, which is this part, and our x-axis. So this whole area right here. That's what we're approximating. So now we're going to talk about our left endpoints and right endpoints. In order to look at these, I'm going to partition each of those squares into their respective areas. So we're looking at those parts right there. And this all the way up here. So now we have squares that we're creating. For the meantime, I'm going to explain our right endpoints because it'll make a little tiny bit more sense. So looking at this square right here that we'll create, the height or at the right endpoint, we're looking at the square here. So we're adding that square, right endpoint here, we're adding that square. All right, so we're looking at this square here, this square here. For this rectangle or this area, we're going to come all the way up here to grab that area. And lastly, this rectangle here. So that would be our right endpoints. We're looking at the rightmost part of that part of the graph to tell us how tall our graph is. And now we did mention something about area. So area, what we're doing is little rectangles, right? So area is always going to be our length times width, especially for a triangle. So area, length times width. So length is actually going to be the height of the graph. So how tall are we going? And our width is how far are we going, like left to right. So notice that the width for each of these is always going to be exactly the same. So in this case, it's really easy to see that. So we're breaking it up into 4 pieces from 0 to 2, half and half. So it looks like we're making pieces of 1/2 each. But to actually give us a formula in order to find that, let's call these the subintervals. So subinterval formula. So subintervals are going to be, we're going to call these delta x. Delta meaning change, so the change in x. So we're looking at the rightmost part of the function that we're evaluating. So from 2 all the way up to 1, or you could think of it as from b or b minus a, and we're dividing it by however many partitions. So in this case, n was equal to 4. So let's find our subinterval for this graph. So delta x is equal to 2 minus 0 divided by 4. 2 over 4 or 1 over 2, which makes sense. We could see that. So starting at the very beginning, so at 0, we move 1/2 over here, 1/2 plus 1/2 gives us 1, 3/2, and then 2. All right, makes sense. So that's what we're doing here. Now there is a different formula for left endpoints and right endpoints. What we call these, we're starting off with the very, very beginning. So x naught is going to be like our very initial point. So our initial point is the leftmost part that they asked us to like find the area over. So in this case, it's 0. So x naught is 0. And in this case, they had us look for or partition the space into 4 parts. So we're going all the way up to x4. So that's x1, x2, x3, and x4. So now looking at that, we have a formula for each of these. So let's start with the left endpoint approximation. So left endpoint approximation. The formula for this one, the area is going to be approximately left n equal to, starting with the leftmost value because we're looking at the left. So leftmost value, so x naught all the way to x1. We have f of x naught, that's how tall we're making it. And length times width, we have the width of our delta x. In this case, it was 1/2. But we continue this until we get to the last box that we created. So that's going to be f of x1 delta x plus f of x2 delta x. And in this case, we're going all the way up to, let's erase this one. This is just a formula. Dot, 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 all the way up to f of x n minus 1 delta x. So why n minus 1? So remember, we only have n boxes. So in this case, we have 4 boxes. So if we look here and here, the next box is going to be from here, the left endpoint here. That's 2, left endpoint 3, and left endpoint 4. Yeah, so we have 1, 2, 3, 4 boxes that we're looking at using the left endpoint. We're using this one here, not the very last one, because the very last one is going to be our right endpoint. So that's why we stop at n minus 1. So the one before we actually finish. So now let's get our stuff ready for this one. So starting off with, so we have L of n is equal to 4, so L4. F of, we're looking at our left endpoint, so x naught comes from the very first value here. So what I'm going to do is do it a little tiny bit differently from the book. I think it might be explained a little bit better. But here we're starting off with A from the part that we're integrating from A to B. So starting off with A, we're adding our delta x. In this case, delta x was 1/2. 1/2, and we're not adding anything, so we're adding 0 of those. So I'm going to multiply this by 0, and that's this whole part right here. Delta x is just that 1/2, so we're multiplying 1/2, and we're going to continue doing this until we get all 4 of our boxes. So the next one, f of 0 plus 1/2 times 1, we moved 1 delta x over. 1/2 plus f of 0 plus 1/2 times 2 times 1/2 for delta x. It's 1, 2, 3, 4. This is the last one. F of 0 plus 1/2 times 3 times our 1/2 times our delta x. What I do notice is that we have the same 1/2 for each of these values. So to make it a little bit easier, and so my hand doesn't cramp up as much, I'm going to factor that part out. So 1/2 factoring out. And let's work on these insides. So we have 0 plus 0, that gives us 0. So here we're looking for the evaluation of 0. Plus this next one, we have 0 plus 1/2. So we're looking at f of 1/2. The next one we have 0 plus 2/2. That gives us 1, so f of 1. And lastly, we have 0 plus 1/2 times 3. That's going to be f of 3/2. And we could evaluate these. Remember the graph of this, f of 0, the function that we're finding the area for is x squared. So we could just plug that right in. So we have 1/2. Plug in 0 squared. So we have 0 squared plus the next one is going to be 1/2 squared plus 1 squared plus 3/2 squared. Again, I'm evaluating each of these parts into our graph here, just to find what value we have for each of these boxes for the left-hand side. Really pretty. All right. So 1/2, adding these together, we have 0, 1/4. Instead of 1, I'm going to say 4/4, just so we can add everything together nicely. Plus 9/4, 1/2, and then we have 10, 14, 14/4. And we could divide those two, that's 7. So here we have 7/4, and that's for our left endpoint. So that's our left endpoint. Obviously we kind of cut it short there. Like here there is some sort of area. We're cutting off all of this area that we see here. So that's, I'm not going to say it's a terrible approximation, but we could do better. Maybe later in the semester we'll learn how to do that part. All right, left endpoint. So we found the left endpoint. Let's find the right endpoint now. So right endpoint approximation. So now for the right endpoint approximation, we're looking at this square here that we would potentially have, we look at the right part of that interval. So the right part of this interval is going to start at x1. So no longer x0, we're starting at x1. So starting at x1, there's that one, there's 2, there's 3, and this time we are ending on our right endpoint, x4. So again, very similar to the left endpoint, just this time it's the right endpoint. Area is going to be approximately our right endpoint, Rn. So in this case, we're starting with x1, not x0. So f of x1 multiplying delta x. Going to f of x2, still multiplying that delta x. And we keep going until the very end, f of xn delta x. So now what does that mean for this value? We have Rn, and in this case, n is equal to 4. We're looking at f of x1 delta x. We did mention that was 1/2 plus x2 Again, delta x is going to be 1/2. And we keep doing this until we get all the way up to x4. And what is that for each of these? So here we have f of starting off with 0. We're adding 1 right off the back. So starting off with 0, we have 0 plus 1/2 times 1. And actually, let's be a little lazy now that we know that the delta x is being factored out. Let's say 1/2 that we factor out. So here we just have f of 0 plus 1/2 times 1 plus f of 0 plus 1/2 times 2. That's the second value. Plus f of 0 plus 1/2 times 3. Plus f of 0 plus 1/2 times 4. Close those brackets. 1/2. This is f of 1/2 plus f of 1 plus f of 3/2 f of 2. The function we're using to evaluate, or the function we're evaluating, is f of x is equal to x squared. So we could grab that and evaluate here. So we have 1/2 squared plus 1 squared plus 3/2 squared plus 2 squared. It's 1/4. Let's rationalize that. So that's 4/4, 9/4, and 8/4. So we have 10, 18, 21, 22, 23, 24. 24/4. That is 6. Goes in 6 times. And goes in 3 times. So our whole solution is 3. Just a minute, I feel like I did some wrong math. I found it. It shouldn't be 8, it should be 16. So again, here we have 4. So it should have been 16/4, not 8/4. All right, one more time. So we have 10, 20, 30. So we have 1/2, 30/4. So 2 divides out with 13, 15 times. So we have that 15/4. Perfect. Now let's compare. Oh, wow. More than doubled. But remember, right now at this moment, we don't have a great way to find that entire area under the curve there. What we're actually doing is approximating. So 1 is going to give us like a way undercut. So the left endpoints, that's 0. We're ignoring all of this. We're ignoring all of this. We're ignoring all of this here. So that's why it's so under. Over here, we're adding all of this. We're adding all of this. We're adding all of this. And we're adding all of this. So one is not better than the other at this point. hopefully later in the future, we could actually find something that will be a lot better to use instead of those approximations. But those are still awesome approximations. If you happen to have any questions, if I didn't explain it properly, please, please, please do not hesitate to ask. And if you understand it, bye.